Okay, so I'm going to be talking about running HTC and HPC applications opportunistically across private, academic, and public clouds. So just starting with a brief overview. First of all, I'll talk about the European Open Science Cloud and explain what that is briefly, and two of the projects that have been working on that, EOSC Pilot and EOSC Hub. Then most of my talk will then be going through the EOSC Pilot's Fusion Science Demonstrator. I'll be talking about what the platform does, how it works, how we're dealing with data and workflows, and then finally a summary and ongoing and future work. So EOSC is the European Open Science Cloud. So I won't read this long description, which is the European Commission's vision of what the cloud is, but a sort of short version is that it's a trusted environment for storing and analyzing data from all publicly funded research. So basically, it's just a collection of services, software, and data that can be sort of accessed in a simple way by all European researchers. So in practice, there have been two Horizon 2020 projects, EOSC Pilot, which has a budget of just under 10 million euros that will be finishing this month, in fact, which is the first phase of the development of the European Open Science Cloud. Then there's EOSC Hub, which started beginning of last year, and it's due to finish in, I think, 2020, which has a much higher budget, and that's basically turning EOSC into something that's actually can be usable by end users. So EOSC Hub is the sort of four main parts to it. It deals with the services, so that's like data, applications and tools, storage and compute services, as well as more people-oriented activities like training and consultancy. Then there are federated services. So these are the services that you need to sort of have behind the scenes in a federated infrastructure. So it's a marketplace, AAI, accounting, monitoring. We then have federated operations. That's about operating the federated infrastructure. So there's like certification of service providers, dealing with SLAs, dealing with customers and managing them. And then finally, there's the processes and policies. So this is all the like security regulations, compliance to standards, and things like that. So the sort of less technical side of things. So one important product that was developed within EOSC Hub is the EOSC Marketplace. So this is a portal that allows users to find, order, and access all of the services available within EOSC. So here I just show the main entrance page, and then an example of when you search for storage system, how lots of different products come up. So it's basically, this is, so all of the products in the EOSC Marketplace were developed within other European projects, and are now available within a central place, which obviously makes things much easier for users. So now I'll move on to the EOSC Pilot Science Demonstrators, which is what I'll be talking about today. So within the first EOSC project, EOSC Pilot, there were 15 science demonstrators. So basically the aim of these is to just demonstrate the usefulness and relevance of all the services available within EOSC. And they come from a sort of wide range of different areas. So there's environment, there's sciences, high energy physics, life sciences, social sciences, astronomy, fusion, and many others. And these are basically just small-scale proof of concepts, which, just, as I said, just demonstrates that EOSC will be useful. So the Fusion Science Demonstrator in EOSC Pilot is called Prominence. Where prominence, the name comes from plasma bursting out from the sun. So now moving on to computing in fusion. So by fusion, of course, I'm talking about fusing nuclei together, and which produces a huge amount of energy. So it's basically about recreating the power of the sun in a very small volume on Earth. And the eventual aim of this is to create electricity, of course. And we are getting closer and closer to doing that. So in the Eurofusion research community today, most of the computing is HPC or HTC oriented, and it basically consists of just isolated islands of data and computing resources. So if you want to access data from a particular experiment, you have to get access to a particular cluster. And from there, you can then access the data like just over NFS. And another issue, so it's difficult to access data and resources at other sites. You just have to SSH into different clusters. And one issue is that the software is not portable. So the software is basically designed to only work on 1 or 2 sites, and then you just have to get access to those sites to use the software. However, things are going to be changing with the advent of ITER. So ITER is the largest fusion experiment ever, and that's currently under construction in the south of France. People say that it's the most complex machine that's ever been built by humans. So this is not yet ready, but it's getting closer. And so the one big difference for the fusion community is that it will generate petabytes of data every day. And that's a lot more than the fusion community is normally used to dealing with. So it's going to be a huge change for everyone. So data is going to have to be distributed globally and able to make use of it, and we're going to actually have need access to much more in the way of computing resources. So in the Fusion Science demonstrator, what we wanted to do is to just address part of the computing problem. So first of all, just how to make use of academic and public clouds for Fusion HPC applications. In some other areas of science, people have been using clouds basically since Amazon first brought out EC2, but in Fusion, it hasn't quite happened so quickly. Also looking at how to extend small-scale on-premises HPC clusters to clouds in order to cope with bursty workloads and sort of provide a transparent way for users to access the resources. And also importantly, try and get the same results wherever you run, which at the moment that's not really possible. So one difference between our demonstrator and the other science demonstrators is that what we're doing is not specific to Fusion. We're just sort of developing a general platform that could actually be used by other people. So data management is obviously very important, just as important as computing, but at the moment we're not, within this project, we didn't really consider data management too much. So we have another project within EOSC Hub, which is the Fusion Competence Center, which will be addressing data handling, things like data distribution, replication, accessing data at different sites. But for the moment, within EOSC Pilot, we're just looking at, well, we're considering a case of individual users rather than sort of central data processing. So just how so individual users can access their data. So all we want to do basically is just to be able to run batch jobs in clouds, and there are many, many existing open source and commercial tools that allow you to do this. Almost everyone seems to have invented some system for doing this. There are sort of different categories, I would say. So, for example, there's clusters on demand. We just generate an entire traditional batch system in a cloud. So there's the head node, the scheduler, some worker nodes, and the storage. There's the cloud bursting method where you have a standard HPC system at your site, and then you burst onto worker nodes in an external cloud, and people normally would have like a VPN so that the worker nodes can access your NFS storage from your site. And then there's the more sort of cloud native ways of doing things where there are sort of workload and job management tools that have some sort of API, and then a sort of message queue or database, and it can then sort of spawn worker nodes, and this can then all run on the cloud or on Kubernetes or something. So it would seem that what we want to do is just sort of fairly straightforward, but it's not quite so straightforward. So within EOSC, there are cloud resources available. So the EGI Foundation, that was created in 2010 to coordinate all of the grid infrastructure for the Large Hadron Collider. So since then, they're still playing that role, but they're also involved in clouds and other activities, and they're actually one of the 3 coordinators of the EOSC Hub project. So the EGI Federated Cloud is a group of about 20 different resource centers around Europe. These are mostly OpenStack clouds, some Open Nebula. So federated in the sense that they all have the same AI infrastructure, so you can log into each of them, you will access each of them with the same credentials, and also like they have the same image names and same images available. But apart from that, they're basically independent clouds. So they all have different endpoints, different flavor names, and things like that. So we were only given opportunistic access to the EGI Fed cloud sites. So, for example, if you just consider resource usage at 4 different clouds, so these plots are just meant to illustrate, so the resource usage is a function of time. So the blue is what's being used by the sort of main users of the clouds, and the green is what's left over. So we just have, all we have access to is just the leftovers, basically. And we have to, so sometimes there'll be no resources available on a particular cloud, other times there'll be lots of resources available. And we just have to find some way of actually making use of those. So we have access to many small clouds, opportunistic access only, so we just have sort of different numbers of cores here and there. And other science demonstrators just sort of picked 1 or 2 clouds, or even their own cloud, and just made use of that to keep things quite simple. But we thought that it would be actually much more useful if we could find a way to aggregate all these resources, and that would then make them more usable and useful to users. So the users didn't have to try and find which clouds have free resources. They could just do whatever they wanted, run their jobs, and that would be taken care of. So this, it seems, I don't think it's a situation that most people normally consider. So then going back to the running batch jobs on clouds, the existing open source tools didn't really meet our requirements. They generally support multiple cloud APIs, but not lots of clouds simultaneously. They just assume you have 1 or 2 clouds with almost infinite resources that are just limited by your credit card. A lot of them assume that the end users have cloud credentials, and also the end users are basically aware that they are using a cloud, so they need to push some button to deploy infrastructure and like decide what size worker nodes to use and things like that. But we didn't want to do that. We wanted to make it all just totally transparent to the users. So then the newer cloud-native job and workload management systems also didn't meet our requirements. Some of those didn't seem to support jobs with different resource requirements, and in particular, they didn't seem to support multi-node MPI jobs, which for us is important. And again, they seem to generally support multiple cloud APIs, but not many clouds simultaneously. So for us, multi-cloud is not just sort of 1 or 2 public clouds, it's having to use many unreliable clouds. So some of them may never work, some of them may almost never work, but occasionally do. Some clouds might sometimes work, and other clouds might mostly work. We just have to somehow make use of all of those clouds. So that's why we then developed our platform, which we're calling Prominence. So the theme of this is submit globally and run globally. And it's designed to enable users to transparently run their applications opportunistically across actually both local and remote HPC facilities, in addition to private, academic, and public clouds. So from the user's perspective, it just appears like a normal batch system. They're not aware that clouds are being used at all, or that they're in different places around the world, and they don't have to worry about infrastructure at all. So one difference we have is, compared to the sort of normal batch systems, is that we decided it would be more useful to have a REST API which interacts with JSON. So that way, users could have a command line utility that they can just easily install on their laptop or desktop, or they could directly interact with the REST API if they wanted to programmatically, or even have a web UI that sort of makes things even simpler. Because one thing we found is that engineers in particular seem to prefer UIs compared to the command line. And then they interact with this one system, and then they can submit and check the status of their jobs, and they can just run all around the world. So one challenge with Fusion software is that, well, the applications are written in lots of different languages, so there could be Fortran, C, C++, Python, Perl, Bash, RDL, MATLAB, and to some commercial, some open source. Some applications actually include all of those languages combined together. Also have different compilers involved, so like GNU, Intel, PGI, and there might be like commercial libraries being used, like, say, the NAG libraries. And they're generally designed to be built and run on only a few specific HPC clusters. So it makes use of lots of modules and the pre-installed software on the different clusters, and there are makefiles for different clusters. So, and if you want to run the code on a different cluster, you can try and do it yourself, or sometimes actually send the developer to a different cluster, and then they will then spend a week or two trying to work out how to get the software to build and run. Another challenge is that there's a wide range of resource requirements. So there's a wide variety of applications, not just science, but sort of plasma modeling, materials research, engineering, design, rendering, so lots of different things. And so an application could range from needing to use 1 core to over 1,000 cores. So then the question is, how do we then enable this software to be run across multiple clouds? So some people seem to actually try to develop complicated systems for installing all dependencies in virtual machines everywhere. But we're not going to do that, of course. It's just been much simpler these days to use a container. So we have to basically then encourage users to create a container image that has the application and all dependencies. So that way the jobs can then reliably be run anywhere, and they will then be reproducible. So we're using 2 different unprivileged container runtimes, Singularity and uDocker from In Your Data Cloud. So for people who sort of used to HTC and HPC systems, these are the 2 most common container runtimes. So from the user's perspective, Prominence just appears to be a normal batch system if you install the CLI. So here's an example of this, submitting a job where you just specify resource requirements if you have any. In this case, it's specifying 2 environment variables and a container image, and then what you want to run. So it's very straightforward, and then you can do normal things you can do on a batch system, like checking the status of a job. You can also do things like check the standard output and error in real time, no matter where in the world your job is running. So the architecture of Prominence is shown here. So we're using, as I mentioned before, we have a REST API, and for the authentication, we're using an external identity provider, which I'll come to in a moment. We're using Condor as doing most of the work, so it's managing all of the jobs and taking care of remotely executing the jobs in a secure way. I'll talk about that in a bit more detail later. And then we have a special placement policy engine, which is what's deciding what clouds to deploy the infrastructure on. Oh, I thought I had more time. And then we're using a tool called Infrastructure Manager to actually interact with the clouds and provision the VMs. So this is just showing that's how we're making use of services and software that's been developed within the other projects within EOSC Hub. So for authentication, we're using AGI Check-in, which is a proxy that allows you to access a resource provider that's using your normal institutional credentials. So that's one of the things that's available within EOSC Hub. So that means any user can then easily access Prominence. The reason why we're using Condor is that, well, Condor was developed a long time ago, back in the 1980s, but it's actually perfect for cloud environments. So unlike things like Slurm and PBS, there's no central list of worker nodes. You don't have to have the same configuration file everywhere. It's designed to handle worker nodes coming and going. And in particular, you can have worker nodes over the wide area network and on the public internet without any problems. You don't need to have VPN or anything. And people have been doing that for many years securely, and it works very well. And it does work at very large scale. So some of the LHC experiments have it sort of running at 100,000 or 200,000 jobs level, and that works well. So it would take a lot of work to actually reproduce all of that functionality, and I'm not aware of any other tools that can do that. So for infrastructure deployments, I'm using Infrastructure Manager from Integrated Data Cloud. That's a tool similar to Terraform for deploying virtual machines on different clouds. So it supports like OpenStack and all the major public cloud providers and lots of others. And it can also take care of contextualization using Cloud Init or Ansible. We make use of both. I'll just move ahead quickly. So one of the most important parts is deciding where to actually provision the resources. So we've have a policy-based resource placement engine that is a layer on top of infrastructure manager that decides where to provision the infrastructure for each job. So we make use of a general tool called Open Policy Agents, and that decides what cloud meets the job's requirements, and then it can rank clouds based on preferences and also determine like VM images and flavors. So one thing that's very important is failure handling. So we basically assume that everything will fail, and then we can have lots of retrying and timeouts and back off from clouds which fail, of course, and then retry in other clouds that meets your job's requirements. And then just this diagram here, you shouldn't expect someone to read it, but this is basically our deployment workflow. So there's lots of steps involving deciding what cloud to use, then determining if we need to get a token to access the cloud, then whether we need to deploy an Ansible node or not, and then actual deployment, and then depending on the status of that, whether we need to try again or try on a different cloud. So it's quite complicated. But what this allows us to do is that we can preferentially use a local cloud, but then we can burst onto other clouds when needed. So we could, say, for example, burst from a local private cloud onto UK research clouds, and then from there, when they're full, burst onto European clouds, and then finally onto the public clouds. But if you need special resources for your job, for example, access to GPUs or InfiniBand networking, then obviously you can just directly use those clouds. So you could burst from one to the other, or you could just, maybe there are two clouds that meet your requirements, so I could try those. Or maybe only a public cloud meets your job's requirements, so it will just skip straight to that. And then just some examples. For example, if you submit a 64-core job and then some 4-core jobs, in this case, none of the local providers or European resources could handle the 64-core job, so that went straight to Google, and then the others ran on the cloud within the UK. Here's an example. Also, the different colors correspond to different clouds. This is bursting from a remote HPC cluster onto an UK OpenStack cloud. Here's just a group of clouds within EGI Fed Cloud being used opportunistically, and then you can do things. Here's an example of using 3 different OpenStack clouds within Europe. And for data handling, we have obviously scratch space for each local to each job, as well as for the MPI jobs, they have shared NFS storage across the nodes running the job. For persistent data, we started off using a sort of stage in, stage out model. So users could upload data and then specify in the job what input files they need, and then before the job runs, that would then get staged onto the machine where the job is running. Then the job would run, and then output data could then be staged back to the same central location. But then we found that users would generally prefer sort of POSIX-like access to a sort of normal file system. So for that, we've made use of 2 EOS Cub services. There's B2 Drop, which is that's based on Nextcloud, so it's sort of Dropbox-like functionality. So you can access data from a web browser as well as from your jobs running on Prominence. And similarly, there's another system called OneData, which is for federating different storage systems, and that also allows users to access data from web browser or their laptop, whatever, as well as from jobs running within Prominence. Okay. So because we can easily access data no matter where the jobs are running, one thing that now allows us to do is to have workflows that can run across multiple clouds. So our initial support for workflows uses something called DAGman, which is available within Condor, which we're using anyway. So basically, users can specify their jobs and dependencies between them, including resource requirements. And then the system will then take care of running those jobs in the correct order. So some of the unique features we have is that you can have HTC and HPC steps within a single workflow. So for example, if you had a first job that needs a single node, that could run first. Then if you have another step that needs multiple nodes because it's an MPI job, those resources would then be provisioned for that job and then disappear afterwards. And you can also have different individual jobs in the workflow can run on different clouds. So, and they can then obviously all access the data that was generated in previous steps. So for example, maybe you have access to one cloud that's InfiniBand networking, so you prefer that the MPI job in your workflow runs on that site, so that can be done, and maybe you have another step that needs GPUs, so that part of the workflow could then be directed to a cloud that supports GPUs. So it sort of gives users lots of flexibility and can sort of make use of any clouds and sort of what features they provide. So to summarize, we've developed a platform that enables users to transparently exploit lots of different cloud resources, as well as existing facilities for running HTC and HPC jobs. And we can use many clouds opportunistically in a very dynamic way. And we can also run workflows across multiple clouds. And in terms of ongoing work, one thing we're doing is we're aiming to make Prominence a production service in the EOSC marketplace. So this way, basically anyone can then access Prominence and try it out just using their home credentials. We want to look at integration with Active Directory, possibly using Keycloak, because, for example, our site doesn't actually have an identity provider. We want to look at integration with private container registries. So at the moment, Harbor looks like the most promising option, but we have to wait for the OpenID Connect support. And also, we're still looking at integration with other storage systems that are available within EOSC Hub. Hey, thank you. Any questions?
Very nice idea, very interesting design. I was wondering, when you schedule the jobs, do you take the cost into consideration, or when you decide to put the compute to a certain cloud, do you consider how easy to access the data, that kind of requirements?
We haven't yet considered how easy it will be to access the data, but that's one thing we'll be looking at within EOSC Hub. And for public clouds, we can sort of just choose the cloud with like the cheapest, that would be the cheapest for your particular job in a sort of very simple way. So we can do things like that. But yeah, the data side of things, that's still work to come, because that's obviously harder.
Yeah.
So. Yes.
Since your applications are distributed as containers, right, with singularity and Infra,
Yep.
it's supposed to run everywhere. But given the huge amount of platforms to support, it runs into problems where some clouds don't run some applications, or they were running them inefficiently.
Well, we have encountered situations where, for example, B2 drop works very slow at a particular cloud, but at other clouds it's much faster. Obviously, a lot of the clouds we use, we don't have any control over the VM images, so that's sort of been sometimes an issue if you assume that what seems to be a standard application is installed, but it's not. But in terms of the Fusion applications themselves, generally that's sort of works relatively well. Okay.
Another question. Let's say when users submit a bunch of jobs and specify the resource requirements wrong, the job will never succeed in any cloud. Can you handle that kind of situation?
You mean if it's too big to fit any cloud, or just it fails?
It fits into any cloud, or they're too small to complete the job.
If they ask for more resources than are available, then it will just fail and give them a message saying that it's not possible to run their job.
Yeah, if they allocate too little memory for that particular job, it's never going to succeed in any of the cloud.
Oh, in that case, yes.
Yeah, in that kind of situation, do you handle that, or you just report back to the users and can run your job?
It will just fail and report that back to the user. I guess we could try and increase the resources requested, but that's not something we've tried. I mean, some people do that. I'm not sure how successful it would be.
Yeah, just curious.
Okay.